Okay, so we're going to do some Lewis structures. Here, we're going to do Lewis structures and we're going to do um, some geometries, molecular geometries, and then all the intermolecular forces. Got a bunch of problems here. You're going to want to have a periodic table available for this. There is one as part of this practice problem set, but I'm not going to be flipping back and forth to it for this. All right, so one of the first things that you can do, you can kind of mix up whether or not you do this first. You can either draw the skeletal structure first. So, for example, here we've got um, nitrite, and since nitrogen is the single element, right? There's only one nitrogen, but there's two oxygens. Always safe to assume that that's going to be the central atom unless we're told otherwise. So that would be my skeletal structure. Now, I also want to calculate valence electrons. So this is the other thing that you could do first. So since we have nitrogen and we have oxygen, nitrogen, we have one of those and we have two oxygens. Nitrogen has 5 valence electrons, and each oxygen has 6 valence electrons. So that's going to be 5 plus 12, plus we have a charge. So that negative charge means that I add one more electron. So if it's a positive charge, we would subtract an electron. It's a negative charge, so we add one. So this is going to be 18 electrons. And if you're taking my class, you did the Lewis structure worksheet, we labeled that VE, so that's the total number of valence electrons. And then we would subtract out the number of bonding electrons in the skeletal structure. Maybe I should change this to be like SBE, skeletal bonding electrons. And so we used 4. So we subtract those out from my total, giving me 14. We call those the remaining electrons. Now, when we replace these remaining electrons, we're going to go on the terminal atoms first, and we're going to give those octets. So it's 2, 4, 6, 8, 10, 12, and then 14. So once my terminal atoms have octets, and that's including the bond, right? So 2, 4, 6, 8, 2, 4, 6, 8. Those are full up. So now I've got extra electrons. I had that extra pair, so I put that in the middle. And then I check to see, does everything have an octet? Well, I already gave these octets, so those are good. But now if I look at nitrogen, 2, 4, 6. So I need to share some electrons. So I'm going to take a lone pair from the right side. I'm going to put that in the middle there to make a double bond between the nitrogen and the oxygen. You could have done the other side. And then we're going to put it in brackets and give it a negative charge because the molecule has a negative charge. If you are coming to this is for an intro to general chemistry class. If you're taking first semester just general chemistry, like a majors level general chemistry class, you would look at formal charges. We will not be talking about formal charges in this video. All right, so let's do the other order here. For this one, phosphorus, we have one of those. We have 3 hydrogens. So this is times 5 electrons. This is times 1 electron. So that's going to be 5 and 3. And we don't have any charges, so we can just add those up, and that's going to give me 8. And that's my total number of valence electrons. And now I'll do my skeletal structure. Again, phosphorus being the singular phosphorus and not multiple phosphoruses. That's probably going to be our central. And so I place phosphorus in the middle, and then I give a single bond between phosphorus and the hydrogens around it. So next we do our bonding electrons, 6 bonding electrons, and I subtract those bonding electrons from the total. So that gives me 2 remaining electrons. Now, when I look at this structure, hydrogen only ever gets a duet, or 2 electrons. So I can't place my remaining electrons on one of these terminal hydrogens. They already have as many electrons as they need. So instead, I just place them straight onto the central phosphorus there. And now we can check and make sure we have octets, or duets in the case of hydrogen. So the hydrogens are all set, each with just 1 bond or 2 electrons. And the phosphorus has 2, 4, 6, 8. So that one's good to go. All right, so next is SO42 minus sulfate. So again, sulfur is by itself, and then everything else, all the other oxygens are going to be around it. All right, there's one sulfur, there's 4 oxygens. Sulfur is my central atom. The oxygens will all be terminal. And so now we do sulfur, oxygen. There's 4 oxygens. Each oxygen has 6 electrons. Each sulfur also has 6 electrons. So it's 6 and 24, plus a charge. 2 minus charge, so I add 2 electrons. So that'll be 30 and 32 valence electrons total. And notice that I'm not like going to the periodic table and okay, say oxygen has 6 electrons and then placing 6 electrons on each oxygen. No, we don't do it that way. This step-by-step method gets to the answer more reliably. So how many valence electrons did I use? 2, 4, 6, 8. I used 8 of them already for bonds. So that's my bonding electrons. I subtract those out. So 32 minus 8, that's 24. And that's my remaining electrons. Now I can go and start placing them on oxygens until each gets an octet. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that places all of them. And again, if you're coming to this from a general chemistry and not intro to general chemistry class, we would address formal charges, but since this is an intro class, we don't do formal charges. We just check to see octets, right? So that's 8, 8, 8, 8. All of my oxygens are good. Sulfur has 4 bonds, which should be 8 electrons. We just need brackets and a 2 minus charge. Okay. So H2S, we can do something similar again. We do sulfur in the middle. Because there's 1 sulfur, there's 2 hydrogens. So sulfur goes in the middle. And then I've got hydrogens, there's 2 of those, times 1 electron each. Sulfur, there's 1 of those, times 6 electrons. So it's 2 and 6. No charges, so we just add those up. That's 8 electrons. Those are my valence electrons. I used 4 bonding electrons. So that means that I subtract those, and then I have 4 remaining electrons. Now again, where do I start placing those? Hydrogen only needs 1 bond. Hydrogen doesn't get any more than 1 bond. So my 4 remaining electrons will go on the sulfur in the middle, 2, 4. That's all of them. And then again, we check for octets or duets for hydrogen. So each hydrogen's already got 1 bond. Those are good. 2, 4, 6, 8 for sulfur. So that would be the final Lewis structure for H2S or hydrogen sulfide. All right. So draw the correct Lewis structures for ClO3. So we do, again, chlorine. There's 1 chlorine, and there's 1, 2, 3 oxygens. So the 1 chlorine goes in the middle, the 3 oxygens go around. Chlorine, oxygen, 3 and 1. Oxygen has 6 electrons, chlorine has 7 electrons. So 7, 18. And then we do have a charge, and it's a negative charge, so it's plus 1 electron. So 7 plus 1 is 8, plus 18 is 26 electrons. So it's valence electrons. And then 2, 4, 6 bonding electrons. So we'll subtract those out because we already used them. So that'll give me 20 electrons remaining, or 20 remaining electrons, Re. Oxygen. Oxygens need them, so 2, 4, 6, 8, 10, 12, 14, 16, 18. Now I got 2 electrons left, so I'll put those on the chlorine. Now I filled up all of my oxygens, so those should all be 8. And my chlorine's got 3 bonds, which is 2, 4, 6, and then the lone pair makes 8. So we've got all octets here. Not thinking about formal charges for an intro to general chemistry class, but we do need brackets and then the charge. You're also not doing resonance structures. Okay, last Lewis structure here, NH4. So again, nitrogen alone in the middle, hydrogens all around, 1 nitrogen, and then for hydrogens, we have 4 hydrogens. Those are times 1 electron each, and this is times 5 electrons. 5, 4, and then our charge. And in intro classes, we don't have very many positively charged ions, polyatomic ions in particular. So this cation, ammonium, has a positive charge, which means that I subtract 1 electron. So I take 1 more electron away, or take 1 electron away. So this is going to be 5 plus 4, which would be 9, minus 1 is 8 electrons. So that's my valence electrons. And then I use 2, 4, 6, 8. So I subtract out another 8 electrons for my bonding electrons, which leaves 0 remaining electrons. And all of my hydrogens, they're good. They've got 1 bond. My nitrogen has 4 bonds, which is 8 electrons. We'll put that in brackets and give it a positive charge. Okay, now moving on to these other problems. For these problems, I guess I will have to flip back and forth between it. The main way that I showed in class to do these is for the central atom. It's always for the central atom. We're counting the number of bonding groups, well, electron groups, so e.g. bonding groups and lone pairs. And then we use a chart to figure out what the geometry is going to be. So for this, remember, bonds of any kind, a single bond or a triple bond, those each count as 1 electron group. So that's 2 electron groups. And carbon, we can see it's attached to hydrogen and it's attached to nitrogen, so that's 2 bonding groups. And then carbon has no lone pairs, so that'd be a 0 for lone pairs. So go down to this chart. Here's the chart. So we had 2 electron groups, 2 bonding groups, 0 lone pairs. The electron geometry is linear. We don't care about that for this problem. It's asking for the molecular geometry, which in this case happens to also be linear. So if I go back up to here, this is linear. Let's fill in linear. Now we want to bubble in all the intermolecular forces present in this molecule. So for dipole-dipole, has to be polar. Honestly, we can go through it on all of these. We should bubble in dispersion because everything has dispersion forces. Ion dipole, we need to have an ionic compound and a polar compound. So we would really need to have 2 compounds for that. Hydrogen bonding, though, would be a hydrogen attached to hydrogen and oxygen, hydrogen and nitrogen, hydrogen bonded to fluorine. Those are the only 3 times that we have hydrogen bonding. So this does not have that. It has hydrogen bonded to carbon, not the nitrogen. So there's no hydrogen bonding here. It's not ion dipole. Is it dipole-dipole? Well, the hydrogen-carbon bond has a different polarity than the carbon-nitrogen bond. So yes, this is polar. And so it has dipole-dipole. On to the next. H2S. So we got sulfur, and again we want to do electron groups, bonding groups, and lone pairs around sulfur. So each of these pairs of electrons, they're lone pairs, it'd be 2 lone pairs. But they also count as electron groups along with these bonds. So that's 4 electron groups. It's 2 bonding groups because there's 2 hydrogens. So if I go and I look at this chart, looking for 4, 2, and 2. Now, tetrahedral, don't get distracted. Tetrahedral is the electron geometry. We're not looking for those. We're looking for the molecular geometry. So bent is the molecular geometry. Now, in an intro to general chemistry class, determining whether or not something like this is polar should be pretty easy. So we will have dispersion forces. And then my central atom has lone pairs. So that will be polar. There will be dipole-dipole. There won't be ion-dipole because we don't have an ion in addition to our dipole. There's not hydrogen bonding because, again, hydrogen-oxygen, hydrogen-nitrogen, hydrogen-fluorine. Those are the only hydrogen bonds that we're looking for. Well, that's where hydrogen bonding occurs, I should say. All right, so next, with this SO4 2-, so electron groups, there's 4, because sulfur has 4 bonds. Bonding groups is 4, lone pairs, 0 for the sulfur. So if I go and I look at my table, so looking for 4, 4, and 0, and the molecular geometry is tetrahedral. All right, so tetrahedral. Now, if we want to determine if this is polar or not, because again, everything has dispersion, is this polar? Does it have dipole-dipole? Well, I have sulfur in the middle here, and then all of these oxygens are the same. No lone pairs in the middle, so it's non-polar, which means it's not dipole-dipole, which means we don't have ion-dipole or hydrogen bonding either. All right, I guess phosphorus tetrahydride, or not trihydride, not tetrahydride. We've got 3 bonding groups, 1 lone pair. So bonding groups 3, lone pairs 1, electron groups is 4. Go look at your own table. Honestly, at this point, I think I'm just going to fill these in. That's a trigonal pyramidal. We have a lone pair, so there is dipole, dipole-dipole. There is dispersion because everything has dispersion. No ions, and those hydrogens are not attached to nitrogen, oxygen, or fluorine. Okay, electron groups, 4 bonding groups is 2, lone pairs is 2. We've actually already seen that one. This one is also bent. And we do have lone pairs on the central atom, so this will have dipole-dipole. And then, actually, I think bent is always going to be polar, so dipole-dipole. And then we always have dispersion forces. We don't have an ion. You need to have an ion and a polar compound. And then we don't have any hydrogens at all, so it can't be hydrogen bonding. All right, electron groups here on the carbon, again, that's 4. So bonding groups, because they're all hydrogens, is 4. And lone pairs is 0. That's a tetrahedral. And then they're all carbons. There's no lone pairs, so this will only be dispersion. It's nonpolar, so it's not any of these. Sorry, you might want to get that a little longer. Okay, so next, electron groups, there's 4. Bonding groups, there's 2. Lone pairs, there's 2. So this is bent again. It is polar, so it's dipole-dipole, and it has dispersion forces because everything has dispersion forces. Not ion dipole, no hydrogen bonding. Did I put anything with hydrogen bonding in here? Oh, I didn't put anything with hydrogen bonding in here. Okay, I'll draw an example. And then I'll add it to the actual one that I uploaded. All right, so we got hydrogen, iodine. Now, this is a special case. When you have just two atoms, if I draw 2 points, what shape can I draw with just 2 points? A line. So when you have only two atoms, when it's diatomic molecule, it's always linear. And we look, see, is there an electronegativity difference between hydrogen and iodine? There is, so this is polar. It also has dispersion. No ion dipole, no hydrogen bonding. Sorry, I'm just checking. Okay. All right. Again, we need electron groups is 4, because we're looking at the nitrogen, so 1, 2, 3, 4. And then bonding groups is 3, lone pairs is 1. This is a trigonal pyramidal. And then because I have a lone pair on the central atom, we will have dipole-dipole, we will have dispersion, we will not have ion dipole or hydrogen bonding. Electron groups, 4. Bonding groups, 4. Lone pairs, 0. That's tetrahedral. And then all hydrogens, no lone pairs on the central atom, so only dispersion forces. This last one's a little bit weird, but remember, we're only looking at the central atom. So electron groups, 2. Bonding groups, 2. Lone pairs, 0. Erase those, they look like extra bonds. That's linear. And there's an electronegativity difference between the nitrogen and the oxygen, which means that this is polar and has dipole-dipole and dispersion. And again, no ion dipole, no hydrogen bonding. Now, need to add another one in here. H and H. Oops, H, something like that. So this molecule, for doing the shape, electron groups would be 4, bonding groups is 3, lone pairs is 0, which means this is trigonal pyramidal. And now I do have a lone pair on the central atom, and I have nitrogen with hydrogens attached. So this molecule would be dipole-dipole because it's polar, dispersion, and hydrogen bonding. So all 3 of those. The only one it wouldn't have is ion dipole. So now I get to go and add that into this problem set.